Joel Friedman from UBC, and he'll tell us about a new interesting approach to proving lower bounds.
Can you actually, is there microphones here? Can you actually hear anything? Oh, okay. I see. Okay.
That's just to take it.
Oh, I see. I see. Okay. To the millions. Pardon? I think so. That's what he said. To the millions of people who want to find out about Grothendieck topologies and complexity theory. I'll now finally have a lecture on the web. Actually,
and they'll make a CD of you too, so that people can watch it again.
Oh yeah, it'll be great watching. There with me and Brad Pitt, I suppose.
Well, you can post it on MySpace.
So, what Uri said was in part true, but in a certain sense, it's a fairly old idea that I'll be talking about today with sort of a new twist. So please feel free to stop me at any point, ask me questions. Maybe that's, I'm used to talking at universities with a lot of students who are very intimidated. And, I assume you've all kind of graduated and realized that sort of everyone just basically gets up and talks nonsense in front of people anyway, so it doesn't really matter. But that's sort of the case here. So the idea is to try to attack complexity theory via what might be called topology or geometry, and so on. Now, complexity theory is a pretty broad term, and in the late 70s and early 80s, people were looking at algebraic decision trees and attacking them by counting connected components of the zero set of a certain function. This is not what I personally would like to do. When I was a student, undergraduate, maybe a few years ago, 3-4 years ago, I guess it must have been, there was an idea floating around that maybe Boolean complexity theory could be tackled also by modeling a Boolean function by some sort of topological data and then taking connected components, Betti numbers, and so on to use to obtain complexity theory lower bounds. And that's basically what I'll be talking about today. Except, so this is sort of this was a dream back when I was a student in the early 80s, and it's still a dream in the 2000s and whatever. But I'd like to explain why the use of Grothendieck topologies may greatly simplify matters and give a much larger class of examples of this. Okay. And I don't think there's any other new idea in the talk, basically. Just a lot of work to try to get some examples. I will give today a toy example where part of this works and you get bounds essentially for a set cover problem, which is not so interesting since it's a well-known bound, but at least it takes some of these ideas and goes part of the way there. So this is the 2-line executive summary of what you'll see today. Are there any questions? Okay, thank you very much. Now you can just ask questions if you like. Are there any questions? I know I'm being terribly, terribly vague.
Yeah, we're
Too intimidated. Okay, well, maybe maybe I should show you, actually start with a Grothendieck topology to show you how unintimidating a thing it is, actually. I usually don't, but what the heck, we'll change things around a little bit. So people think that this is a very vast and powerful set of tools developed by Grothendieck, and they're right, but there are many simple examples that are rich, simple examples that you wouldn't have in regular topological spaces. So let me start with this so that people won't be so intimidated, and then I'll get to the main thrust, which is to explain this toy example in the complexity theory, and try to explain a little bit about the relationship. So the examples. By Grothendieck topology, I'll look at the very, very special, very special case where you basically have a finite category with certain properties. So you have a directed graph. You can have multiple edges between vertices in this graph. And you'll always have exactly one self-loop from every vertex to itself. So it's a directed graph. With a composition law. How many people know what a category is at this point? Okay. So maybe I don't have to say very much about it. The composition law means that if you have two arrows, there's a distinguished composition of the two arrows. So for example, if you're going from node A to B to C, and you combine these, you're supposed to pick out an arrow that is composition, thinking of these as sort of objects in some sense, and these arrows as functions. In this case, there are two arrows from A to B, so you actually have to specify something. So when there's more than one arrow between two vertices, this specification of the composition law becomes interesting. And the upshot between Grothendieck topologies and regular topological spaces will be that in a regular topological space, you only have one arrow between two vertices. And in Grothendieck's view, you can have, amongst other things, more than one arrow and get a much richer class of examples.
So now if what if I look at the arrow from A to A and then the composition of the arrow from
Yeah. In this case, there's only one. Now, if I had two of these, then there would be a question. But let me tell you about the. So. Okay, but let me say what kind of composition. I want it first of all, it has to be associative. So the path of length 3 is there's a unique arrow associated. Secondly, there have to be identities. So these loops that you have here don't affect the arrow under composition. And there'll be one or two other. Oh, question? Yeah, in the sense that I don't really want to get into, I think, unless I have to. So maybe I'll take that at the end this time. But no, it's a valid question. Well, the open sets, actually the open sets are the sets of vertices that are closed going backwards. So this, I mean, in this case, there are no more sets than there are, well, there's an empty open set, and then each one of these vertices is an open set associated. But in something, you know, like a square or something like that, it'd be different. Okay. So there's a few other assumptions I want to make, such that it's finite, and each vertex has one self-loop. But aside from that, that's all I'm going to assume about the graph and the category structure. Right. Exactly. So that subloop has to be the identity, and there's nothing else. And if you have more than one, you can start basically doing group theory and group cohomology in this setting. And then a lot of the things that are true are no longer, that I would like to be true, won't be true anymore. So I have to make some, this is a very general notion. Here we're starting with some simple restrictions. Maybe, 5 years from now, if I still have the energy to do this, and I don't get anywhere, maybe I'll allow more, maybe I'll try to incorporate group cohomology into it. But as a first approximation, I take the simplest thing that seems to have enough structure to do something with. Any other questions? 90% of the time, you can say you have a directed graph. And if you want to take the cross product or fiber product, you can just take it as graphs, and the composition law follows along automatically. So, and open sets are just defined in terms of the graph structure and so on. So for most of the stuff, it's okay. When I define sheaths, which I'll do on the next slide, then you have to remember the composition law a little bit. So there are aspects for which it's crucial to know the composition. So I'll define the notion of a sheaf. So for every object, there'll be a vector space, and the arrows will simply go the other way. So I'll take, say, the 3-dimensional reals, the 5-dimensional reals, and the, 2-dimensional reals for each vertex. I'll reverse the orientation on all these edges, and I'll insist that you have a linear map associated to each arrow that maps between the spaces. That preserves the composition law. So if this composed with this is this arrow, then this arrow has to say the composition of these maps. And this is all the topological data I will use in the entire talk. This, to me, is topological data. Yeah. You could. So I don't have to, when I'm drawing this graph, there's a lot I don't have to do. If I've drawn this and this, well, I know I have self-loops, so I don't have to draw them. The composition I know exists, so why bother with that? Now this has an extra one, so you should have some sort of memory symbol that says that this is a new one that doesn't occur there. But in this, you'd confuse me. Yeah, you want to draw all the things which are. Yeah. Well, yeah. For this talk, you would be lucky. For this talk, you could get away with that, actually. But in general, you couldn't. If an arrow has more than one factorization, then things start to get ambiguous. Like if this arrow came from this and also from this and this, you'd have to know that those two compositions were the same. You'd have to remember that. And that's going to be important. Well, because it turns out that in this toy example, all I'll use is what's called a free category, which means that you take a graph and you look at all the paths in the graph, and those are your edges. In that case, just by drawing that graph, you can reconstruct the whole thing just by taking compositions of everything. So, I don't want to say that the category has to be free and limit myself completely if I don't have to. So, okay.
Actually, you have to tell us a lot more which of these arrows, which composition.
Yeah.
Almost like a book, big table.
Well, in fact, it is a group. In fact, if you take a single vertex and you take a bunch of arrows, and you assume that each arrow has an inverse, then you've completely done finite group theory in this. This is why I say I don't want this situation, because group cohomology can be infinite even for very simple situations. So I don't want to do this here. Not in 2006, and probably not in 2007, to the foreseeable future, unless I can, you know. But yeah. Other questions?
So the sheath, does it, when you draw this picture, does it mean distance, or does the sheath specify?
Oh, the sheaf specifies a map. So here you'll have a matrix, and here you'll have a matrix, and so on. So each object you have a vector space, each arrow in the reverse direction you have a matrix.
So now you don't have to do composition.
Right, because we know there. Pardon? Yeah, just a linear map, yeah. I mean, it's true. Back to this case, you just get basic group representation theory. Yeah. But I wouldn't, you know. Yeah. So you have a Grothendieck topology. You have basically, as long as two things can multiply together to get the identity, all of the formulas get a lot more complicated. There's a certain simplification. You can throw out, if the identity stands alone, you can basically ignore it.
Oh, wait, so you asked, so when you said directed graph composition is associated with identities, you also require that no two arrows, the composition of no two arrows is identity.
That's,
Did you ask that in addition?
yeah, I did, here.
One.
Oh, wait, okay. Yeah, I sort of did. If you have, this is okay, as long as the composition of this is the identity. But then the composition of this and this will have to be the identity. And then these two objects will be isomorphic. So if you collapse, if you have so-called a sober category, where the only thing you're isomorphic to is yourself, you can essentially throw this away. Then you will have then what I said will be true. But you're right, it's not true in general.
So when you think you simplify identifiers,
There are situations where actually this is a little bit more convenient to do. So I wouldn't rule this out, but for most of the proofs of the theorems, it's just a nuisance to have them in there. So you allow this or not according to convenience, basically. Okay. So now we have Grothendieck topologies, and we have sheaves. And from these two concepts, we can start to get invariance. Pardon? I sort of did up here. Okay, so the definition of a Grothendieck topology is you have a category, and then the sheaves on it are for each object you have a vector space, for each arrow you have morphism, and then there are the localization requirements. Now, what localization am I thinking of? I'm thinking of the absolute silliest one. Well, not the silliest one, but there are two extremes. One where everything is required, one where nothing is required. In my world, nothing is required. So I'm taking the grossière topology, or what he calls la topologie grossière or chaotique. So it's a very simple one, but it's not. It still is interesting. It still is very interesting. In fact, if you take any topological space, I'd rather than give this definition, because to say what localizing mean, I mean there's two axioms. I probably couldn't reproduce them off the top of my head. I can tell them roughly what they mean, but to go through this definition would take quite a while. I mean, it could do it in by the end of the talk, but I don't know what if you learn a whole lot from it. The other way is you can take it that I have slaved through reading all this stuff and distill for you the following examples of Grothendieck topologies, where you can essentially think of, for all practical purposes, just a graph with a composition law category, and with certain restrictions, and where the sheaves come out to be everything that you don't have no further condition other than for each object a vector space for each arrow composition. This would take long. I'm happy to do it offline, but it'll take a while. It's actually a talk about complexity theory and Grothendieck, and trying, usually I spend 10 minutes on this, and then I start off with complexity theory. But having started with this, maybe we'll spend more than 10 minutes on it.
Well, I guess
The covering the covering conditions are vacuous. I mean in a topology you have to specify the sheaf generated by the object itself is always in there, and if nothing else is in there, then that's called the grossière topology. And that's what I have. It has no localization requirement. You don't have to look at anything else here and say that certain things locally have to be reconstructible globally. That's right. Sheaves and pre-sheaves are the same thing through this talk. Now, I think I started to say there's actually a reason why I do this, and that is that if you take a topological space, you can actually always assume that you get something like this by eliminating certain vertices. So this is not as incredibly special as it may seem. Any topological space can be realized in this form, I claim, by throwing away all the open sets except the irreducible ones. So this is not so incredibly specific. But right. That's what I like about it, is that it is finite. The structures that I encounter in discrete math are finite structures. And if you're telling me that you have some, manifold, some fancy structure that's going to model it, I'll say maybe. But, these seem to be able to model discrete things better. All finite topologies, yeah. Okay. Other questions? Okay. So from Grothendieck topologies and sheaves, we can start to get numbers. Such as a Betti number sum. And maybe others, I don't know. And these will hopefully provide lower bounds in complexity theory.
So who had this string?
Well, this was done for algebraic decision trees by Dobkin and Lipton, and then Steele and Yao, and then Michael Benor. And I was sitting in a class by Les Valiant, and he sort of mentioned this. And Michael Rabin was at Harvard at the time, so somewhere between everyone, there was sort of this hope that this would yield something. And I don't know how seriously people took it, but when I started reading the works of Grothendieck, I started realizing that the topologies he's dealing with are much more general if you have, say, multiple edges. But they still have all of the same features of regular topological spaces, just about. So I was sort of inspired to try to take a look at this. And now I'll describe my little toy example that goes some of the way to do this. Okay, ready for a toy example. So here is the question. I was sitting in the car with Les, and at some point he said, you're trying to do ands and ors, and nots, but if you just had, say, ands and no knots, then it wouldn't be a theory at all, would it? And I sort of thought, and I said, well, maybe it would be actually, a simple theory, but a theory nonetheless. So the theory of Boolean complexity theory with just ands, okay? I'll describe it in terms of...
Like a teenager's dream.
Yeah. Yeah, there you go. And. I usually write it in terms of set theory, but maybe I'll try it in terms of ands and see how it comes out. Should I try it in terms of ands, or should I try it in terms of set theory? Who wants set theory? Who wants? The set theory approach is easier for people who aren't used to complexity theory.
Do the
Scratch.
set
Okay.
theory.
I remember I heard it. The set theory approach is that everyone, who does complexity theory is saying, oh, you really mean the characteristic function of the set. Oh, you mean and, you don't mean intersection, It just looks kind of... I mean, when I had it explained to me... Okay. I remember I was at IBM, and Ingo Wegner was visiting, and he started explaining all his complexity questions in terms of set theory. And I thought, boy, these Europeans have a bizarre way of describing complexity theory. And I thought that was the difference, but not all Europeans do it that way, I guess. Okay, so we start with a set, S. We have the power set is what? 2 to the S, T of S. You can choose this one. This I can do myself. 2 to the S, okay. You have some basic sets that I will call F1. And now you want to see, for a given subset of S, you want S itself? Oh, no. Leave. You want S underlined?
He's trying to be different.
I see, okay. So I'll take the minimum number of sets in F1 that I need to intersect to get A. So that A is F1 intersect Fi, and such that all the F's are in F1. I'll call this a size. So the sets themselves are of size 1. The intersection of any 2 of them that's not in the set itself is of size 2, and so on. How many sets, okay? So for complexity theory, this may look like a toy question. So size is NP complete, first of all, to compute. Secondly, there's a lower bound for size. Which is given by a linear programming bound, which is just the relaxation of the integer programming bound. And it's not too far off from the truth. Oops. So it's off by a factor of log of the size of f1 at most, which depending on your application could be disastrous or could be not so bad. Not so bad. If f is of size 1, then I guess everything is of size. It's either of size 1 or infinity, basically. Let's forget 1, okay? 2 or more. Okay. Now the complexity angle on this is that this would basically do a very, very big thing in a certain special case as follows. The size of A is the minimum over all values h of A where h is a function from 2 to the s to the non-negative reals such that h of b is less than 1 if b is in f1, and h of b intersect c is less than h of b plus h of c. Well, it's not so hard to prove. So it may look a little.
Well, explain.
Okay, I'll explain it. So let me explain it. So first of all, h equals size works over there. So if h is the size function, then it's true that the size is no more than 1, and the intersection of any two sets has size that's no more than the sum of the sizes. Because the size would definitely work. And secondly, I don't know, h of b1 intersect b2. Less than 1.
Oh.
Yeah, h can be 0. Oh, I'm sorry. You're right. Little tiny mistake here. Max. There we go. If it were min, it wouldn't prove lower bounds. I want to prove lower bounds. And if you take the intersection of two of these guys, if b1 and b2 are in f1, then their intersection is less than b1 plus 2, which is less than or equal to 2. And so by induction, you can easily show that the size works and anything else can't be bigger than the size. Okay. So this is called a formal complexity measure. It tries to measure size complexity. Maybe it doesn't get it exactly, and it only gets a lower bound, but it has some of the approximate properties enough to lower bound size. So the size is always bounded from below by any one of these particular h of a's. So now all you have to do is pick an h, compute h of a if you can, and then you get a lower bound. It's just that simple. Okay. Let me relate this to standard complexity theory. let's take S to be a hypercube. Let's take the distinguished functions to be the empty set, everything, and then the coordinate half plane. So coordinate half cubes, let's say. Obtained by taking one of these n coordinates and fixing one of its values. So then this looks like the Boolean functions 0, 1, and the literals and their negations. Now, let's say you take the max over h of a such that blah, 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 as before, and you add in the condition that h of a set and its complement are the same. Here's a strange European way that Ingo Wegner was explaining complexity theory to me. Then you're bounding size, formula size complexity of the associated Boolean function. So this is the same thing as formula size, which is essentially up to a constant factor, well, the log of this, log of formula size is essentially the same thing as circuit depth. This to hold for every b, yeah. Pardon? Yeah, it's slightly different. Okay, slightly different. The intersections correspond to taking ands. So I'll have a tree where the intersections, the ands are charged for, but negation, you're never charged. And then an OR is a negation, two ands, and a negation. No, negation and two negations. So ORs and ands cost the same, and this is essentially equivalent standard complexity theory. All you have to do, now I spent most of my, yeah, that's a condition I spend a lot of time studying. Because when two numbers are equal, if they come from topology, then it often either comes from the topological things being the same or else some sort of duality theory. And that duality theory to me, I thought was the key. I spent a long time on this, developing some duality theory. And I simply couldn't get this duality theory and various ideas for this combined at this point. So I was able to get an idea for this to work with topology. I mean, there is, of course, a cheat in everything. I mean, the number 17 is represented by 17 points, right? In terms of its sort of topological complexity. 17 connected components, nothing else is going on. So any number that you want to, any concept, I mean, you can sort of express with this general notion of what h should be. But the idea is that this should come from a topological reason. And if you can incorporate it, maybe this should come from another topological reason. Or something. I mean, you know. Well, let's say I say, okay, I can take h to be formula size. And formula size is a very, very hard thing that a lot of people would like to know about. It'll separate NC classes if you know it well, probably. So a lot of people would like to know about formula size. Now, I can just say, okay, I can take h to be the formula size and represent that topologically. If the formula size is 17, I'll get 17 points. And that's a topological representation of that concept. But the reason why this would be true and this would be true wouldn't be from a topological reason, and you wouldn't be able to compute that on any reasonable example. So the other thing is you have to be able to compute these things. You must be able to compute them, or else they're just concepts. So this is what you must for a concrete A, for A of interest, like an A that represents an NP-complete problem, or maybe not NP-complete problem, some interesting question. You must demonstrate to me what that value is. If you can actually compute it, because I could just say, oh,
get a lower bound, or
to get lower
Yeah.
bound, yeah, to get lower bound. You don't have to compute the class of all the h's. You don't even have to, for a given h, compute it on every single a. In fact, as a varies, you can vary your h. In here, you don't have to. If you were omniscient and you just took formula size, but in what I do, I will vary essentially the h depending on the a, which is different than what I expected. I expected, well, you'll just know everything, and you'll do, if you want to do formula size, you'll do something that will still work for everything all at once. But in this toy example, it doesn't. You have to vary the h given the a. So, okay. All right, so this is what we really want to do, and today I will do this. I will eliminate this negation condition, and but if you eliminate the negation condition, this becomes a pretty easy problem. What can you get by intersecting half cubes? Well, quarter cubes, eighth cubes, and so on. Okay. An interesting thing is that there are sets that can't be represented as intersections, and those sets have infinite size complexity, and these geometric topological methods will give you infinite size complexity. So that was something that I sort of didn't expect, actually, until I did this example. Well, infinite, I simply mean it can't be written as the intersection of the sets. Okay. Oh, it's, well, I mean, this is all of these are finite questions. Yeah, to decide, it's not hard. I mean, in fact, the linear programming bound gives you the feasibility of the linear program. I mean, the simple answer is, let's say I have a set A. So anything that I intersect to get A had better be bigger than A. And then maybe, so the things have to be bigger than A. So I'll throw away anything that's doesn't contain A. And then all the points in my universe have to have the property that there's at least one set that what do I want to say here? Whose complement contains it, yeah. So that it's cut away from everything. So there isn't one point here that belongs to this set and this set and this set. And forgive my sloppy drawing. I don't have dancing PowerPoint presentations yet. Okay. So that's the set. But it's NP complete, and it's not a trivial problem. And I'd like to demonstrate, just in very rough terms, how a linear programming bound comes up from the topological situation. Okay? Any questions before we? Oh, I mean, the linear program is either feasible or not feasible, and accordingly, I mean, that's an alternative way. It's probably not as good a way as this is, but you know, it's either feasible or it isn't, and that's to be checked. Okay. So we'll leave complexity once and for all, forget this, and now we'll just go back to this situation here. Now, rather than say too much about Betti numbers and so on, why don't I tell you the graphs, the categories that I use? Because that may give you a feel for what's going on.
But then at some point,
Briefly, how I have another 7 minutes for my. I'll let you ask questions. To show that if I look at the size as the number of intersections for this sets in F1, then I'll get the linear programming bound in a simple way with a simple situation. Okay. So let me give first the Grothendieck topology. So you take for S. Let's assume that S has size 2 or 3 so that I can draw it. So you take all the subsets of S. Let's say S is 1, 2. And I'm going to take the paths on this graph. So the paths, again, have 4 vertices. And there's one path from any 2 sets that include each other. There's a path of length 0 at every set, and then there's 2 paths of length 2. One that goes this way and one that goes that way. Okay? So just the monotone Boolean directed cube, and you take a look at the paths. There will be any vertices of distance 2 or more in the cube will have more than one path between them. This won't be a standard topological space. Now I'm going to take 2 sheaves. So for A, I will associate 2 sheaves. Call it F and G sub A. The first sheaf won't depend on A. And in fact, it doesn't matter what its arrows are at all. All that matters is what are the dimensions of the vector space. So there'll be R to the, I don't know, A, R to the B, R to the C, R to the D. And these, you just don't care about them. It's not going to matter what they are. They could be the 0 map. Yeah, whatever this could be the 0 maps. You could put in 0. Whoops, and I'm going the wrong way, of course. Okay. The dimensions, these variables will be, in fact, the variables of a linear program. So there will be, as long as they're non-negative, any non-negative integers. And then it'll be a linear program with integers, and then I'll normalize and take them to be rationals and take them to limit and so on. The sheaf G sub A is formed by taking is formed by starting with a basic sheaf. Now it's going to depend on what oh, I shouldn't use A actually. I should use B because A is the thing that we're trying to A is the thing that we're trying to find an interesting H value of here. So G of B will be as follows. Let me assume that A is the empty set. That's the most interesting case anyway for this. I've given you F as sort of a variable.
No, about the basic set.
The script F's?
F1.
The script F's are good question. I'm going to take a moment. The script F's are arbitrary. Yeah. No, that's a good question. No. Here's what's going to happen. We're going to have a linear program. A linear program has a whole bunch of inequalities. It has an objective. The objective will be here. All the linear inequalities in the linear program will be written in terms of conditions on the F's. Okay? So the F's are going to occur in the linear program after we write down the Roman F. Well, in this case, I never get to all the details anyway, so I try to give you a flavor of what's going on. So you may be waiting a long time if you want to hear, in the next few minutes, but this situation is written up in a 7-page paper that I just posted. So it's not too hard to see what's going on in this situation. Although it uses the 70-page paper that I wrote to explain all this stuff. So, okay. Anyway, so let's assume that A is the empty set. What I will take is I will take R, and R squared. The number in the exponent comes from the number of edges there are between the two objects. Okay. This is called, for those of you who know, this is called an injective sheath. It's a very simple sheath that has no interesting cohomology except in degree 0. No interesting cohomology. And I will take this and sort of destroy all the interesting things that could happen here and get the linear programming bound. So if this seems like some sort of crazy recipe, it's actually a very standard recipe. And then to a set B, I'll look back on my cube, and I'll basically take this sheaf G, except maybe if B is over here, I'll take it to be G in here and 0 outside. So I will just take almost the same sheaf G, except I will cut it off by 0 outside the things that lie beneath the set. I remember, perhaps my favorite teacher was Professor Bott, who passed away recently. And at one point, he was teaching a class, and he said, you know, extension by zero. And he went over that, and he said, now you sneered at extension by zero, and you sneered, but now I will show you how wonderful this thing is. And I always have fond memories of extension by zero when I think of Bott and the way he would talk and his charisma. Anyway. So extension by zero looks like a very benign thing, but it's actually a very powerful tool in sheaf theory. And it allows you to relate what's going on here and maybe what's going on here to everything together by putting everything in one context, in one larger context, and then zeroing out to restrict to those sub-open sets or whatever they are. So if you've never seen extension by zero before, don't be fooled. It's not something to sneer at. Anyway, so to B, we associate the space F and G of B, and now H of B, by definition, is what I call the Betti number sum on FGB. Okay. So by Betti number sum, I mean, how many people are familiar with the Betti numbers? Okay. So essentially, what this means is that given two sheaves, there are natural groups called the X groups, which in the case of constant coefficients represent the number of connected components and the classical Betti numbers. And this is a slight generalization that appears to be needed to make this thing work. So what is essentially what would be the Betti number would be the dimension of an X group, and if you sum those together, you will get a number, a positive number, and that will be my value for H. Seems like a lot of work to go for a linear programming bound that's not so hard to derive, but for me, what this means is that some of these topological ideas can be used to get somewhere, at least in complexity theory. When I spoke about this stuff December, Harvard, so before December, I had no idea that any connection at all could be made, and now I've made a toy connection, so maybe in a few years from now I'll make a more interesting connection, and maybe not. So perhaps I'll stop here.
This is probably understood. What made you choose Betti number sum?
No, it's something I haven't said yet. I haven't said, and if you want, I'll just say for a minute. This, I think it's, kind of like Passover. If you plant the right questions, then the thing goes much, much longer, and you get a lot more lecture out of the. So.
Did you like time?
No. You do what you can with kids. Mine are 9, 7, and 5. I mean, it's just like kind of out of control. But okay, so let me call the complexity of two sheaves to be the Betti number sum. Which is the sum of the dimensions Okay. That's this number here, Betti number sum. Okay? The idea is that if G1 is the quotient of G2 by G3, and you look at these numbers, G1, G2, G3, and you take the sum, and it has to be the sum, and you can't weight the sum, it has to be the sum, then these three numbers satisfy triangle inequality. And the triangle inequality that I was looking for is H of B intersection C is that's a triangle inequality. Yeah. So this is the triangle inequality here means is the device used for this. And you know, it's sort of, I mean, always the case with a short exact sequence and a long sequence. Then if you look every third in a long sequence and sum of them, you get a triangle inequality. And that enables you to bound the complexity of bigger things by smaller things if they sit in that relationship.
And is there some variance that says that is the only thing that will have that?
No, I don't know. I don't know that there is. It's the one that I'm most familiar with.
Invariant, so
Yeah.
right. So
Yeah.
So, I mean, for me, a question that I would want to ask right away, because you would want to get H's better bound.
Yeah.
But since you have using invariance, if you look at all of the invariants in space, and say, okay, well, this is what invariance, what combination of invariants?
Right. Yeah. I think that I was so stuck on this idea of the Betti numbers and the Betti, you know, like that. If you take the Betti numbers themselves, then to get a triangle inequality, just out of the Betti numbers, I think you'd pretty much have to take their sum. I mean, I'm not. At least for a simple. I mean, the other thing is, you know, what do you want? Do you want HBC less than HB plus HC? Well, what if you had a 2 here, you know, or a half here? Would that, I mean, in the purest form, this is what you'd expect from formula size. But if you had other numbers here, you could still maybe get a bound. So then maybe you could take, you know, the 0th dimensional Betti number and twice the first, then 4 times the second, and so on. So there's some room to play here. But, you know, there's so much room to play, it seems, in what I'm doing that I try to pick something very specific and hone in on it. And, pardon? Well, that's a good question. If the graph, if you look at the number of arrows and vertices in the graph, then you can write it down. See, the one that I showed you here has exponential and s edges, maybe. And if s is itself exponential in n, then it's doubly exponential. And then in essentially linear in the number of arrows, you can write down these concrete computations to do these. So they may be doubly or triply exponential, or more or less depending on the model. But when I, you know, fit it to conditions like this, I typically get something doubly exponential. I mean, singly exponential in s may be doubly exponential in the exponent. Well, easily for a human, not, you know, for a computer necessarily. I mean, I know this is Microsoft, yes, and computers are all powerful, yes, but, you know, I mean, humans sometimes can do things, at least in special cases, that computers can't do. Like if you want to compute h of b for every single b, maybe, you know, good luck. I mean, all the Boolean functions, how are you going to understand every single Boolean function? If you have a specific one and you have an h, you know, then maybe a human can actually at least get a lower bound on what the sum is, to get a lower bound on. I mean, the goal is to get an interesting circuit size lower bound. In a paper, you know, of some reasonable size, you know, enough that it could be accepted to a journal or something like that. You know, so. But there's no, I mean, and in principle, they always are finite computations, in principle. But in practice, it doesn't have to be. In fact, in practice, if you believe the Rasborov-Rudish work, then you may not expect it to be singly exponential in that view, at least if you're going to do P versus NP, which is one more step beyond this, which is one step behind what it wants to be anyway. So. You know, I always think about the duality theory. I really love the theory, and I think that it's the most natural, because to say that a function and its negation are going to be modeled by the exact same thing, I don't believe it. And to say that it's just going to be a pure coincidence that they're going to be, that their Betti number sums are going to be the same, I also don't believe it. And I believe, you know, that the duality theory might explain it. And it's such a pretty theory. But it's hard to get it to work with extension by zeros, because it, I don't know, well, hard for me at least so far. So I don't know, but I think it's, you know, when do two Betti number sums equal, other than, you know, pure luck or isomorphism? This is sort of a screaming, you know, situation where it does, and it's so. I think it's worthy of investigation. But I'm also glad that Les in the car said, well, what if you forget negation? What happens? You know, you don't get anything interesting. Oh, yeah, that's right. Okay. I'd certainly like to put negation back into it if I could. And I would still try duality. I don't know any other. Maybe I'm wrong. Yeah, yeah. I mean, it's so, you know, when you take ands or ors, you just take an and and or. But the negation of a function is a natural thing. You have a function, 1 minus the function, it's the negation. It's just there, you know. It's not going to go away. And in every complexity theory, essentially, the function of negation has the same complexity. So that's something that, you know, that's why I spend a lot of time on it, but wasn't getting as far as I'd like to.
Why do you say it's
Oh, I mean formula complexity. It's written a formula or a circuit of a Boolean function. Yeah. That's a good point. Deterministic.
Yeah. We don't